Swayam Prabha. Digital India. Educated India.
In the last lecture, we were talking about the general equations in the 1D and 3D case as well as 2D. So let's try to simplify the equations for 2D analysis, because that's what we are going to spend a lot of time, and the equations will be simpler. And once you understand the 2D, you can extend it to 3D much easily. So let us spend some time on the equations related to 2D solid mechanics. So what do we mean by 2D solid mechanics? So 2D solid mechanics, as we know, consists of two dimensions, x and y, and so there's a plate here, and one so there are two cases that come under the class. Is that one thing is the plate is thin, two cases here. So obviously, basically, we would like to deal with two variables only. We want to, and we have two displacement components, u and v, at every point p here. Every point p here will undergo deformation u and v, which are functions of x, y. And so there are only x, y are the variables, and are the independent variables on which the solution depends. So here the two cases are, one is plate is very thin, and of course it's a plane. Let us say xy plane. So we deal with xy, and the plate is thin, and the load and displacement boundary conditions are in xy only. And so we are assuming that it's thin in the z direction, or there is not much variation in the z direction. Okay, so this is the, so if you have, like the example is we keep giving that a thin plate like this, subjected to in-plane loading, and there's a hole here. So here every point P here will have two displacements, and that's what we have to solve for. Okay, so this comes under the class of thin plates, and it's also called the plane stress. So this is a plane stress problem. So taking this plane of the plate as xy, and z is normal to that, then the stresses in the z direction are 0. So that means essentially we have no forces being applied in the z direction. There's no force being applied in the perpendicular to the plate. There's no force in the z direction, and no no boundary conditions either. So that means that the stresses are only in the plane. So in the sense that we have sigma x, sigma y, tau x, y. These are only non-zero, and the other stresses like sigma z, tau x z are zero. So sigma z is the stress coming normal to this plate, and tau x z and tau y z are like in the plane on tangentially on the outer plane. So these are also non-existent. So essentially you have sigma x, sigma y, tau x, y non-zero, and then we have these things are zero. So in the constitutive equations, in the stress-strain relationships, if you put down these conditions, then you can simplify the constitutive equations, will simplify okay, and then I think I'll leave it to you. So out of those 6 relationships, you put down these things, and then you will have the relationship between. So you can extract only the 3 stress components, sigma x, sigma y, tau x, y, and one new So the relationship between the 3 stresses, sigma x, sigma y, tau x, y, and the 3 strains, epsilon x, epsilon y, gamma x, y, are related by these material constants, Young's modulus E and Poisson's ratio nu, right? So this is called a plane stress problem, in which case the stresses only in plane are non-zero, the outer plane stresses are zero. This is a kind of assumption, I would say, is that sigma z is zero throughout the plate. That's what we assume. But essentially, sigma z is zero on this side of the plate, and sigma z is zero on the other side of the plate on the surface. And in between, we assume that it is also zero, because from one side of the plate to the other side of the plate, it's very thin. So there cannot be much buildup of sigma z. Okay, so that is why it is kind of assumption that sigma z is zero in the plate. But however, for thin plates, it is a valid assumption. Okay, all right. So this is what the relationship between stresses and strains. So essentially, so the other things, important things are the for the sake of completeness. So these are strain displacements. Okay. And the governing equation, now we'll have governing differential equation, or slightly one variable less or one equation less, and we have only 2 equations, dou sigma x by dou x, dou tau x y by dou y, plus x bar is 0, and So these are two equations, two in number, right? There are two equations here in the x and y direction, okay? And then what is the other thing that's required is the boundary conditions. So the boundary conditions, of course, this is the stress strain, this is the strain displacement, and this is the stress governing equations. And then the boundary conditions can be on displacement prescribed. U can be U bar and V can be. So this is the displacement on gamma U. Okay. And apart from this, so we have the traction boundary conditions here. So here these equations are also slightly simplified. So we have sigma x and x and tau x y and x, sigma y and y. So these are the traction boundary conditions. Okay, so we have boundary conditions, the displacement prescribed boundary condition on gamma u part of the boundary, and gamma t, the traction boundary conditions, are Tx bar and Ty bar are defined, which are related to the variable stresses in this manner. Then the stresses can be written in terms of strains, and strains can be written in terms of displacements. Okay, that's the definition. This is the complete set of equations for the plane stress problem, right? There is also another class here, that is plane strain. Plane strain is so wherein the three strain components in the related to z direction are 0. So that's epsilon z is 0, gamma xz is 0, and gamma yz is 0. So this is the case where you encounter, in the case of constraint in the z direction, like this is the often so if you have a problem like this, x and y, so this is a long dam, the same cross section. So this is a kind of dam, so which is long. So this kind of situation occurs whenever the cross section xy is extended in the z direction and it's extruded. So like in dams and all that. In long dimension objects with same cross section, like here, we take the cross section to be in the xy plane, and you can see that the same cross section is there everywhere. Same cross section is there everywhere. So that means that that's number one. Number two is that assuming that this is very long and then the ends are constrained. So we know that the W is equal to 0. The displacement in the Z component is 0. So which leads to the sigma Z being 0, as well as, so here the displacements U and V here are only functions of x, y. You can see here any point here in this cross section here. So there is a point P here. So this point P will have the displacements only in x and y direction. So it's not a function in the Z. So this also implies gamma xz and gamma yz being 0. So that way, in these kind of problems where we have the same cross section kind of extruded in the Z direction, and then we are also assuming that even the loading here, the loading which is, say for example here, which is being there, so that's also important. The load and displacement boundary conditions are independent of Z. So this is also a contributing factor when none of the applied loads here or even the boundary conditions like here are functions of Z. So that means that so every cross section here, all the variables are independent of Z, including their displacements here. So that way, the strains epsilon Z as well as the strains gamma xz and gamma yz are also 0. Okay, so that way, this is another very important class of problems. So that means that whenever there is a cross section which is very extruded, very long in the perpendicular to the cross section, so then and everything is independent of Z, so then this is what's going to happen. The only thing here that's different from plane stress is the constitutive equations. So applying these three conditions on the strain in that constitutive equations, get simplified as sigma x, sigma y, and tau xy is E by 1 plus nu 1 minus 2 nu 1 1 minus nu 0 1 minus nu 1 0. Okay, so that if you simplify it and write it in terms of stress and strain relationships, so this is how it looks like that. So the only difference between the other things like the boundary conditions here and the boundary conditions, the traction boundary conditions, they are essentially same. So essentially, if you look the two problem formulations, so the only thing that is different is the constitutive equations. So the relationship between stress and strain, here it is E by 1 minus nu square 1, nu 0, nu 1 0, 0 0 1 minus 2 2, whereas here it is sigma x, sigma y, tau x y, and it is E by 1 plus nu 1 minus 2 nu, and 1 1 minus nu 0 1 minus nu 1 0 0 0 1 minus 2 nu by 2. Okay, so that's how. I'm sorry, there is a very small difference here. Please, there's a very small relationship here. Please make this change. 1 minus nu 0, nu 1 minus nu 0, 1 minus. Please make this a small change. So the solution of the stress strain will look like this one. Okay, so thus we have seen the 2D problems can be put almost very similar to each other. Okay, the stress displacements will remain same. The even here I did not write the equilibrium equations, so the equilibrium equations will be same. Okay, except that the constitutive equations will be different. Okay, and if you want, we can even combinedly put it as the sigma x sigma y tau x y. So combinedly the plane stress and plane strain can be described by equilibrium equations, same equilibrium equations. Okay. And then you have the displacements or just functions of x, y, and strains are related to displacements, or same. Okay, and then the relationship here, sigma x sigma y, combinedly put as the matrix of D. Okay, so here we replace this constitutive equation by the matrix D. Okay, and then apart from that, the boundary conditions are all same. Okay, so that way we can combinedly put it same thing. So I wrote both the equations, set of equations, just at one place, and you can only see all the equations are same except that this relationship is different. Of course, you also have to remember, in the case of plane stress, the stresses in the z direction are 0, and whereas in the plane strain, the stress components in the z direction are 0. Okay, so that is the course which you have to remember. Okay, so now let's go to the finite element formulation. So these are all the governing equations. So now let's go to the development of finite element equations for these cases. So the development of finite element equations in, say, let us say, in 1D case to start with. So this is not difficult. So this is very simple. So there's a load P here. Okay, so that's the axis. So we have here the displacement is ux, and the governing equation is d dx of AE by du by dx plus q. So q is the distributed load. Okay, so the weighted residual statement statement. So we can write it as weighting function Wi so this plus q. So this is the residual in the governing equation 0 to L. And so to this we also add the boundary condition. So AE du by dx plus P, sorry. Here the boundary condition is AE. We have seen this, so is P. I'll put minus P here. Okay, so this is the weighted residual equation, and we have gone through this in the case of heat conduction or even the same problem earlier, and then this will come out to be doing the integration by parts. So we have this, we can separate these two terms. I can put the hat here. The procedure is all quite same. In fact, we have gone through this deriving the weak form a number of times. So this, I'll just go through quickly. I'll separate out. So it is dw by dx, AE du by dx. I'll separate this out. This is the distributed force component, and Wi prime is the another weighting function. So just to recall the conditions on u hat. So if you want to simplify these terms, one of the things is that you can simplify by choosing Wi prime as minus Wi. So by choosing that Wi prime is equal to minus Wi, we know that it can be cancelled with the one of the boundary terms here, the top boundary term, and so the boundary term gets cancelled. It's cancelled, Okay. And so that leaves minus Wi AE du by dx at x is equal to 0. So the top at x is equal to L got cancelled, and du hat by dx. So this is this term, and plus and this Wi minus Wi plus, so that means Wi times P at x is equal to L. Okay, so this is the weak form. I think we'll stop it at this point, and we'll take this equation and then further develop it as finite element equations when we subdivide the demand 0 to L into a number of parts. Okay, we'll stop here.